Carbonyl groups undergo two typical types of reactions: nucleophilic acyl addition reactions and nucleophilic acyl substitution reactions. Like the name suggests, a nucleophile reacts at the acyl group to do addition on the double bond between the carbon and the oxygen, or a nucleophile replaces the group Y that is attached to the acyl group. It substitutes the group Y. To know which one of these reactions will take place, we need to look at the equilibrium that is established if the leaving group Y is substituted on the acyl group. We've seen something similar before. In illustration 45, we saw that it is not easy to substitute the OH group of an alcohol because the OH group creates an OH minus when it is substituted. The OH minus is a strong base, and it means that the equilibrium favors the reagents. So the moment that a leaving group forms a strong base when it is substituted, the reaction will favor the reagents and not a lot of that substance will be formed. It will not be very reactive. So in the same way, we can use these equilibrium ideas to know if we will have substitution at the acyl group or addition at the acyl group. So figure 72 gives an equilibrium reaction where the group Y, the leaving group, is substituted by a nucleophile. The equilibrium is determined by the basicity of the group Y. If Y is a good leaving group, then the group Y minus this will be a weak base. If Y is not a good leaving group, if it's difficult to substitute, it will form a strong base. Y minus will be a strong base. So this can be determined by looking at the pKa value. Let's just look at an example of a reaction like this. So in this case, we have an acyl halide. In this case, the halide is chlorine. And the chlorine atom is substituted by OH minus. So the group Y is Cl. This is the leaving group. The OH minus is the nucleophile. The OH minus replaces the Cl, so we have a carboxylic acid, and the group that is split out is Cl minus. Cl minus is an extremely weak base, so the equilibrium in this case will favor the reagent side. We know that Cl minus is a very weak base because its conjugate acid, HCl, hydrochloric acid, is a very strong acid, and a very strong acid always have a very weak conjugate base. So if we look at the summary of these results, we see this in table 17. We see that the carbonyl compounds that are most reactive are those with the leaving group that is easiest to substitute. Those leaving groups Y that will form the weakest base. So the acid halides, splitting out halide atoms, these are very weak bases because their conjugate acids are very strong. So it is easy to react a nucleophile with an acid halide. And carboxylic acids are also relatively strong acids, and the salts of carboxylic acids thus are also good leaving groups. So the acid halides and the anhydrides are the most reactive organic compounds with carbonyl groups if we look at nucleophilic substitution reactions. Then there's a thick line, and this divides the more reactive and the less reactive carbonyl compounds. These compounds that are less reactive form strong bases when the leaving group Y is split out. So esters, carboxylic acids, and amides form strong bases. And we know these strong bases because we have learned them when we looked at nucleophilic substitution of haloalkanes. So the ethoxide ion, the hydroxide ion, the amide ion were the strong bases. So salts of alcohol, salts of water, and salts of ammonia are actually very strong bases, and they are not good leaving groups. Where conjugate acids are very weak acids, water, ammonia, and alcohols, and this is indicated by a larger pKa value. It becomes larger progressively. So the least reactive compound is the amide. It's still possible to replace the NH2 with something else, but it's quite unreactive. It's got a very large pKa value. Completely unreactive towards nucleophilic acyl substitution are these two compounds, the carbonyl compounds with an H attached to the acyl group and a carbon group attached to the acyl group. The aldehydes, the ketones. In the case of an aldehyde, we have a leaving group that will form an OH minus, a hydride ion. It is an extremely strong base, and because it's such a strong base, it has an extremely weak conjugate acid. Hydrogen gas is not an acid, and it's indicated by this very large pKa value of approximately 40, estimated to be about 40. So it's impossible to substitute the H on an aldehyde, and in the same way, it is impossible to substitute the the carbon group in a ketone. So ketones and aldehydes behave differently from the rest of the carbonyl compounds, the rest of the acyl groups, acyl group compounds, and we see that they undergo addition reactions. So when it's impossible to split out the group Y because it forms a very strong base, we do addition reactions. Aldehydes and ketones thus undergo nucleophilic acyl addition reactions.